Hello there, and welcome to the Sleepy Space Channel. Tonight, we'll be drifting into one of the strangest, gentlest corners of cosmic time, the world of black dwarves, the patient, fully cooled remnants of stars like our own Sunday. They are real, they are predicted by physics, and not a single one exists anywhere in the universe tonight. The cosmos is simply too young to have made one. The first will not appear for roughly a quadrillion years, in a sky that has long since forgotten what starlight looks like. We'll walk slowly through what they are, how they form, why the wait is so unimaginably long, and how the entire universe, including the sun outside, wherever it is shining now, is quietly, steadily on its way to them. If you enjoy drifting off to space, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, there is nothing you need to do but settle in. Let your shoulders soften. Let your breathing slow. Allow your eyes to grow heavy. Let the day fade away. Let's begin. There are objects in this universe that have not yet had time to exist. Not because they are rare, and not because they are hard to make, but because the cosmos itself is still young, still finishing its first long thought, and the patient ending it is moving toward has not yet arrived. The black dwarf is one of those objects. It is the final form of a star like our own sun, the last quiet shape that small and medium stars can take after they have finished burning, finished glowing, finished cooling, and not a single one exists anywhere in the cosmos tonight. You can stand under the night sky on the calmest evening of your life and know, with great confidence, that every white dwarf you cannot see is still warm. Every cooled stellar remnant ever made is still slightly radiant. The universe is only about 13.8 billion years old, and a black dwarf takes far, far longer than that to form something on the order of 1 quadrillion years, which is to say roughly 100,000 times the present age of the universe. The first arrivals have not happened. The first ones will not appear for a long, long time. The universe is, in this gentle sense, still on its way to them. It is a strange and beautiful idea. The black dwarf is a real physical prediction. The laws of thermodynamics insist on its existence. Every white dwarf that forms in a galaxy will, given enough time, become one. The cooling curves are well understood. The composition is well understood. The size is well understood. The temperature it must reach is well understood. The only thing missing is the time. We live too early. The cosmos has not yet aged into the era in which black dwarves are ordinary. So tonight, we are going to walk, slowly, through the long road that leads to them. We will look at what they are made of, how a star becomes one, why none have appeared yet, what the universe will look like by the time the first one finally does appear, and how this whole patient process is already quietly underway in every white dwarf currently glowing across the sky. Our own sun is on this road, and so is every other ordinary star you can see. The cosmos is not running out of time. It is, if anything, only just beginning. To start, it helps to settle the simplest question. What, exactly, is a black dwarf? A black dwarf is what a white dwarf becomes after it has cooled all the way down. It is the last form of a stellar remnant, the dim, quiet, fully equilibrated body that is left when there is nothing more to lose. The interior is mostly carbon and oxygen. The surface is a crystalline lattice of those same ions frozen into place. The mass is roughly that of the Sunday. The size is roughly that of the Earth. The temperature is whatever the temperature of the universe around it happens to be, give or take a little warmth from the long, slow drip of physics that even ancient objects cannot fully escape. A black dwarf is not a black hole. It has not collapsed. Its atoms have not been crushed past the point of recognition. It is simply a stellar corpse that has finally matched the temperature of the cosmos around it, a cooled-down white dwarf, a star-shaped lump of carbon and oxygen at peace with its surroundings. It does not pull at light. It does not warp the sky around it any more than any other sun-mass object would. It simply exists, gently, without glowing. You might already be sensing the gentleness of all of this. There is no drama in a black dwarf. There is no violence. There is no terror. The universe is simply taking its time, and the time it is taking is enormous, and we live near the very beginning of that taking. From here, every step toward a black dwarf is a step into a deeper kind of stillness. The first cooling, the second cooling, the long red phase, the long infrared phase, the slow crystallization, the final settling, each step is slower than the one before. The universe is, in its quietest sense, building these objects in slow motion, and we are watching the first early frames. The word black in black dwarf is not perfect. A black dwarf is black, only in the sense that it no longer emits visible light. It is not a pure absence. It still has mass. It still bends space-time in a very small, very local way. It still leaves a tiny gravitational footprint. And in the very deep future, when the cosmic microwave background, the relic glow left from the early universe, has cooled to far below a Kelvin, even a black dwarf at a few Kelvin will be very gently warmer than the sky around it. It will, in that distant cold, radiate weakly into space, not as a glowing star, but as a softly warm point against an even colder background. This is one of the small, unexpected facts about black dwarfs. They are not perfectly invisible. They are not perfectly cold. They are, in the long view, the warmest things in a very cold universe, not because they are themselves hot, but because everything around them is colder still. There is a kind of dignity in that. The universe, in its old age, is dim almost everywhere, and the black dwarfs are the small points of remaining warmth. You might wonder, listening to this, where exactly a black dwarf sits in the family of stars. It is worth taking a moment to place it. Stars are organized, more or less, by their birth mass. The smallest of them, the brown dwarfs, are too small to ever properly fuse hydrogen. They are not really stars. They are warm bodies that never lit. The smallest true stars are the red dwarfs, which fuse hydrogen very slowly and live for trillions of years. Stars, a little larger than red dwarfs, including the Sun, are called sun-like stars. They live for billions of years, fuse hydrogen at a steady pace, eventually swell into red giants, shed their outer layers as a soft glowing nebula, and leave behind a small, hot, dense core, a white dwarf. The most massive stars do something different. They burn through their fuel quickly, end as supernovae, and leave behind either a neutron star or a stellar mass black hole. The black dwarf belongs to the Sun-like family. It is the last act of a star that was born ordinary, that lived for billions of years, that finished its life by exhaling a soft planetary nebula, and that left behind a white dwarf to cool. A red dwarf, given trillions and trillions of years, will eventually take this same path, but the path will be slightly different. The most massive stars never become white dwarfs at all, and therefore never become black dwarfs. They take a different, more violent ending. The black dwarf is the gentle ending. It is the ending of a star that lived calmly and died calmly and is now, very slowly, going to rest. There is one more soft fact worth holding before we go further. The universe is, in a sense, only one tick into a much longer clock. The first stars formed within the first 100 million years after the Big Bang. The first sun-like stars to die left behind the first white dwarves something like 13 billion years ago. Those white dwarves are still glowing today. They have had almost the entire age of the universe to cool, and they have only just descended to surface temperatures of a few thousand Kelvin. Compared to the cosmic background at 3 Kelvin, that is still extraordinarily warm. They still have an enormous distance to fall. So the first black dwarves are very, very far away from us in time. They are not in our sky tonight. They are not in any sky anywhere. They are still being made slowly, quietly, by the steady cooling of the oldest white dwarves and by every new white dwarf that joins the population. The cosmos is, in this exact moment, in the long middle of a process whose endpoint is the black dwarf. The first one will appear when the universe is so much older than it is today that you would scarcely recognize it. Tonight, you are listening near the beginning of the story. Let yourself settle into that idea for a moment. The universe is patient. It is patient enough to wait 100,000 times its current age to finish a single class of object. It is so unhurried that the very first black dwarves are still ahead of every event that has ever happened. And it is, somehow, exactly that patience that makes the black dwarf so deeply restful as a subject. There is nothing about it that asks anything of you. There is nothing about it that needs to happen tonight, or this year, or in this century, or in this millennium, or in this geological age. The black dwarf is the universe's long exhale, and it has scarcely begun. So we will walk slowly through what it is, and how it forms, and why none exist yet, and what waits at the end of the road. There is no hurry. The universe is not hurrying. And if you drift off somewhere along the way, that is, in a quiet sense, exactly the right response to the subject, the black dwarf is the deepest sleep a star can take, and there is plenty of time for both of you to settle. It can help, before we go any further, to settle into the deep contrast between what the universe is doing now and what the black dwarf represents. The night sky tonight is a sky of warmth. Every visible star is glowing. Every distant galaxy is full of glowing stars. Even the cosmic microwave background, which is the relic glow of the very early universe, is still detectable as a faint warmth in any sensitive instrument that points in any direction. The cosmos is, in this moment, a luminous place. There is light coming from almost everywhere. There is heat being produced by countless trillions of nuclear fusion reactions in countless trillions of stars. The universe is bright. It is bright in a way that it will not always be. A black dwarf is what happens to one of those bright things when there is nothing left to do. It is the end of the warming. It is the end of the glowing. It is the end of the production of new light by that particular object. The carbon and oxygen of the black dwarf were made inside a star that once shone with the same kind of light as the Sunday. The matter is the same matter. The arrangement is the same arrangement. Only the warmth is gone. The object has stopped being something that produces light and started being something that simply exists. And it does that when it finally arrives, very quietly, without ceremony, without observation, without anything in the surrounding universe necessarily noticing. That is one of the gentlest aspects of the subject. The black dwarf is the universe at its most uneventful. It is not a thing that happens. It is a thing that arrives. There is no moment, no flash, no transition, no observable point at which a white dwarf suddenly becomes a black dwarf. There is only a continuous, gentle, almost imperceptible cooling that, at some moment, defined more by convention than by physics, has crossed the threshold of what we are willing to call completely cold. The naming of the moment is, in a real sense, more for our convenience than for any difference in the object itself. The object has been on its way for an enormous span of time. The crossing of the threshold is just one more soft step in a journey that does not stop being itself when it arrives. You might let yourself rest in that for a moment. The cosmos does not mark its quietest events. The patient endings happen without applause, without acknowledgement, without anything else in the universe stirring to greet them. The first black dwarf, when it finally arrives, will arrive in a sky that has long forgotten the kind of light it once produced. There will be no observers. There will be no instruments. There will be only the slow, gradual matching of the white dwarf's temperature to the temperature of the very cold sky around it, and the corresponding transition into a state that finally deserves the name. The universe does this kind of thing on its own time. It does not need anyone to be watching. It does not need anyone to know. And yet, here we are, tonight, knowing about it in advance. That is one of the small wonders of physics. We can describe an object that does not exist. We can predict its temperature, its density, its composition, its surface structure, and its eventual fate, all from the physics of objects that do exist and that we can observe. The black dwarf is, in this sense, one of physics' clearest examples of a foreseen object. It is forecast by everything we know about cooling, about thermodynamics, about quantum mechanics, about stellar evolution. The forecast is reliable. The arrival is certain. Only the timing places it out of our reach. So we will continue this slow walk through the long road, gently, with no particular hurry. The cosmos is in no hurry. The white dwarves are in no hurry. The black dwarves are not waiting anxiously to appear. They are simply on their way, in the soft, patient manner that the universe seems to prefer for its quietest outcomes. Let the night settle around you. There is nothing about this subject that asks for your alertness. There is everything about it that gives permission for rest. To understand what a black dwarf is, it helps to start with the white dwarf that it used to be. A white dwarf is the exposed core of a sun-like star that has finished its life. When the star ran out of hydrogen in its center, it began burning helium. When it ran out of helium, it began producing carbon and oxygen through the fusion of those helium nuclei. It became unstable, swelled into a red giant, shed its outer layers as a soft, glowing planetary nebula, and left behind a small, hot, dense ball at the center of all that drifting gas. That small, hot, dense ball is the white dwarf. It is the seed of the eventual black dwarf. The interior of that core is mostly carbon and oxygen, the ashes of the helium fusion that ran in the star's middle age. Above that carbon-oxygen interior, there may be a thin layer of helium, and above that helium, a thinner layer of hydrogen that was never burned. Some white dwarves have these envelopes, some do not. But the heart of every sun-like white dwarf is carbon and oxygen, packed extraordinarily tightly. When you imagine that packing, you are probably picturing something denser than ordinary matter. You would be right. A typical white dwarf, and therefore a typical black dwarf, since the matter does not move, has a core density of about 1,000,000 grams per cubic centimeter. A sugar cube of black dwarf material would weigh roughly the same as a small car. The matter is so tightly packed that the rules of ordinary chemistry no longer apply in the usual way. Atoms have lost their independent identity. Their electrons have been squeezed out of their atomic orbitals and now move freely in a sea of charged particles around the carbon and oxygen nuclei. The matter is described by physicists as electron degenerate, which is a precise way of saying that quantum rules, not thermal pressure, are doing the work of holding the object up against gravity. This is the most important structural fact about a white dwarf, and therefore about a black dwarf. The reason a white dwarf does not collapse into a neutron star or a black hole is not because it is hot. It is not held up by the pressure of motion. It is held up by a quantum rule that says no two electrons can occupy the same state at the same time. When the electrons get packed too tightly, that rule begins to push back. The pushback is called electron degeneracy pressure, and it is what keeps the white dwarf in shape. Importantly, this pressure does not depend on temperature. It works just as well when the object is cold as when it is hot. That is why a black dwarf, which is by definition fully cold, does not collapse. It is held up by quantum mechanics, not by warmth. That fact alone makes the black dwarf a very different kind of stellar end state from anything you might be imagining. It is not a husk. It is not slowly slumping inward. It is fully supported, structurally complete, and structurally permanent on any reasonable timescale. The shape it has when it first becomes a black dwarf is, more or less, the shape it will keep forever. The matter inside is locked. Only proton decay, if it occurs at all, can slowly disassemble it from within, and we will come to that in a later part of this walk. A typical black dwarf is about the size of the Earth. That is, its physical diameter roughly 13,000 kilometers across, give or take. And inside that Earth-sized sphere, it holds something close to the mass of the Sunday. About half a solar mass for a black dwarf descended from a star like our own. Up to a little over a solar mass for the most massive descendants. The matter is so compressed that you could fit a star's worth of stuff into the shape of a planet. That is not an exaggeration. That is the literal structure. If you could somehow stand on the surface of a black dwarf, and you could not, because the surface gravity would crush you instantly, you would feel a gravitational pull roughly 100,000 times stronger than what you feel on Earth. A grain of sand would weigh as much as a small package. A glass of water would weigh as much as a large car. The whole local environment would behave in ways that have no human analog. Even light, escaping from such a deep gravitational well, would lose a noticeable amount of energy as it climbed out a small redshift, far too small to be a black hole effect, but still measurable. The black dwarf is, in this sense, almost a black hole. Almost. Not quite. The matter is dense enough to do strange things with gravity, but it has not crossed the line where gravity wins entirely. Now, the surface itself. As a white dwarf cools, the carbon and oxygen ions inside it eventually slow down enough to settle into a regular crystalline lattice, the same kind of geometric arrangement that ordinary atoms take when a liquid freezes into a solid. The interior of a sufficiently cooled white dwarf is thought to be crystalline. The cooling literally freezes the inside. And at the surface, that crystalline structure forms a kind of solid skin, a thin shell of carbon and oxygen in a fixed lattice, with the deeper interior also crystallized beneath it. This crystallization is not just a curiosity. It is a real, physical event with measurable consequences. When the carbon-oxygen plasma freezes, it releases a small amount of latent heat the same kind of latent heat that water releases when it freezes into ice. That released heat slows the cooling of the white dwarf gently, like a small thermal blanket draped over the cooling process near the end. Astronomers have, in recent decades, found evidence for this slowing in the cooling curves of certain white dwarfs. It is one of the small ways the universe gives us hints about what black dwarfs will be like, even though none yet exist. The crystal lattice itself is exotic. The carbon and oxygen ions arrange in a regular pattern that, in some models, includes ordered layers of pure carbon and pure oxygen, separated by their relative weights. The lattice is far from any earthly diamond, but the picturesque idea has stuck around that the cores of cooled white dwarfs and the bodies of future black dwarfs are vast diamond-like crystal balls, planet-sized, drifting through space. The reality is more complicated and less poetic than that the lattice is its own thing, not literally diamond, but the intuition is right. The inside of a black dwarf is a solid, ordered, frozen structure. It is the most rigid object the universe knows how to make at planet scale. Around that crystalline interior, the thin envelope of helium and hydrogen that some white dwarfs carry will gradually cool and settle. There is no atmosphere in any meaningful sense. There is no weather. There is no convection bringing fresh material to the surface. There is no fusion happening anywhere. There is no source of new energy. There is only the slow leak of remaining heat into the cold of space. And that is the entire physical picture of a black dwarf. Earth-sized, half-sun massed, carbon-oxygen interior, crystalline lattice, held up by electron degeneracy pressure. No fusion, no new energy, no atmosphere worth naming. A small, dense, silent, structurally complete relic of what was once a star. You might notice that this picture is so still, it almost stops feeling like a star at all. That is, in a sense, exactly right. A black dwarf is what a star becomes when it has nothing left to do. It has finished burning. It has finished glowing. It has finished cooling. The only thing it does, in the very, very long view, is sit there and exist. It is the deepest stillness a piece of matter can reach without collapsing. Even so, there is something quietly remarkable about that stillness. The matter inside a black dwarf is the same matter that was once at the center of a star. The carbon was made in the helium burning phase of the star's middle age. The oxygen was made in the same process. Some of the heavier elements scattered through the envelope were made in the slow burning of a red giant. Every atom in the body of a black dwarf was, at some point, in the middle of a sun. It is the same matter, frozen, finally at rest. The universe has not added anything to it. The universe has only given it time. And it is worth saying again that none of this exists yet. Every black dwarf we are imagining tonight is a future object. The carbon and oxygen of those future bodies is, right now, glowing in the cores of white dwarfs all over the Milky Way. The crystallization is, in some of them, just barely starting. The cooling has many more long, slow stages to go. The shape of the future black dwarf is locked in by the present white dwarf, and the present white dwarf is still warm, still settling, still on the long road to becoming the thing we are describing. So you can think of the present universe as the early shaping phase of every future black dwarf that will ever exist. The matter is already in place. The structural rules are already in place. The cooling is already underway. Only the final temperature has not arrived. The universe is taking its long, gentle time to deliver it. Let your shoulders soften with that thought. The thing we are describing is locked in already. It is on its way. It is not something the universe has to invent or struggle to produce. The cooling is already happening in the quietest possible way, in white dwarves all over the sky. The black dwarf is the destination, and the cosmos is, in its own slow rhythm, walking toward it without ever rushing. It can help to dwell a little longer on the strange, beautiful structure of a black dwarf, because the details are themselves restful. The interior of a fully cooled black dwarf is a crystal, but not the kind of crystal you would recognize from any earthly mineral. Earthly crystals are arrangements of neutral atoms, with electrons firmly attached to their nuclei, and with chemical bonds holding the whole structure together. The interior of a black dwarf has none of that. The atoms have been stripped of their electrons. The bare nuclei float in a sea of free electrons. The arrangement that forms when the object cools sufficiently is a lattice of positive nuclei held in place by the surrounding negative electron sea, in a configuration that physicists describe as a Coulomb crystal. It is a crystal made of charged particles arranged by their mutual electrical repulsion, with no chemical bonds at all. The lattice that forms is geometrically ordered. The carbon nuclei sit at one set of regular positions. The oxygen nuclei sit at another. Some theoretical models suggest that the heavier oxygen nuclei sink toward the center and the lighter carbon nuclei float toward the outside, producing a layered structure with an oxygen-rich core and a carbon-rich outer region. Other models suggest a more uniformly mixed arrangement. The detailed structure depends on how quickly the cooling proceeds, on the precise composition of the parent star's core, and on the influence of trace heavier elements that may also be present. In every case, the result is a single, planet-sized crystal, a kind of cosmic mineral with no atmosphere, no surface activity, and no internal motion. The thermal properties of this kind of object are themselves quietly fascinating. A crystalline body cools differently from a liquid body. The free electrons in the interior carry heat efficiently. The crystal lattice carries heat less efficiently. The combination of fast electron heat transport and slow lattice heat transport produces a cooling curve that is well understood theoretically and that has been verified indirectly by observations of the present-day white dwarf population. The slowing of cooling as the lattice forms, the small plateau where latent heat is released, the gentle resumption of cooling once the crystallization is complete, all of these have been measured in real white dwarfs and are exactly what theory predicts. This is one of the small reasons the entire picture of black dwarfs is so well grounded. The physics that will eventually produce them is the same physics we can observe in action right now in the white dwarfs of our own galaxy. There is nothing speculative about the structure. There is nothing speculative about the cooling. There is nothing speculative about the destination. The only thing that is even slightly speculative is what happens on the longest timescales: proton decay, piconuclear fusion, the very late physics, and we have set those aside for a later part of this walk. The basic body of the black dwarf, as we have just described it, is essentially settled physics. There is something gentle in that too. The universe is not asking us to imagine an exotic object. It is asking us to imagine the cooled-down version of an object we already know. The white dwarfs of our galaxy are real and well studied. The cooling road they are on is real and well studied. The destination is the natural endpoint of that road. The black dwarf is, in a real sense, not a new kind of object at all. It is just an old kind of object, given a great deal of time. The exoticness is in the time, not in the physics. You might find that reframing reassuring. We are not waiting for the universe to invent something new. We are waiting for the universe to finish doing something it has always done. The cooling is ongoing. The crystallization is, in many white dwarves, already underway. The next stages will, in due course, follow. There is no missing step. There is no required event. There is only the steady passage of time, applied to objects that are already doing exactly what they need to do. Let your breathing slow with that thought. The body of the future black dwarf is already, in a real sense, present in the white dwarves of tonight. The structure is locked in. The matter is in place. The cooling is in progress. The only thing missing is the patience required to let it finish. And the universe, gently, has more than enough patience to spare. A white dwarf does not become a black dwarf all at once. It does not flicker out or change form or pass through a single dramatic transition. It simply cools. That is the whole story. The cooling is the road. It is slow at the start, slower in the middle, and unimaginably slow at the end. And somewhere along that road, the white dwarf passes through every color of starlight, drops below the threshold of visible light entirely, and finally settles into the temperature of the universe around it. When it does, the cooling is essentially over, and the object is, by definition, a black dwarf. It helps to walk through the stages one at a time, because the road is long, and each step has its own quiet character. The first stage is the youngest white dwarf, fresh from its planetary nebula phase. The exposed core is extraordinarily hot surface temperatures of 50,000 Kelvin, 100,000 Kelvin, or in the youngest extremes, even more. The light it gives off at those temperatures is brilliantly white, faintly blue. It is the kind of light that picks out clean, sharp shadows. The white dwarf is small but blindingly hot, a tiny searchlight at the heart of the planetary nebula that just dispersed around it. This is the brightest, hottest, youngest version of the object. From this moment forward, the only thing it will ever do is cool. The cooling at this stage is rapid, by white dwarf standards. The hot object radiates strongly into space, losing energy through its surface like a coal pulled out of a fire. Over a few 100 million years, the surface temperature drops by tens of thousands of Kelvin. The color shifts gently from white-blue toward yellow-white, then toward pure yellow. The light still illuminates the surroundings. The object is still very much visible to ordinary instruments. This phase is the dominant phase of the white dwarfs we observe in our galaxy today. Most of them are in or near this temperature range. The second stage is the yellow and orange phase. The surface temperature has fallen into the range of a few thousand Kelvin, somewhere between 5 and 10,000, depending on age and mass. The white dwarf now glows in the same range of colors that an ordinary star does, but with one important difference. It is so much smaller than an ordinary star that its total light output is feeble. A yellow-white dwarf has the color of a yellow star and the brightness of a faint candle. It is a sun-colored object that no longer shines like a sun. The third stage is the red phase. The surface temperature drops below about 4,000 Kelvin. The light shifts toward the red end of the spectrum, then toward deeper reds. The object becomes increasingly dim. Even a large telescope would struggle to see it at galactic distances. The matter inside has not changed. It is still carbon and oxygen, still electron degenerate, still planet-sized and sun-massed. The only thing that has changed is the surface temperature. And the only thing the object is doing is leaking heat into space. It is during this red phase that crystallization typically begins in the interior. The carbon-oxygen plasma deep inside reaches a temperature low enough for the ions to settle into a regular lattice, and the freezing process slowly works its way through the core. The latent heat released by that freezing slows the cooling a little. The cooling curve develops a gentle plateau. From the outside, the object looks almost the same as it did before, only dimmer. From the inside, an extraordinary structural transformation is taking place. The slow ordering of trillions upon trillions of cubic kilometers of carbon and oxygen into a single, planet-sized crystal. The fourth stage is the infrared phase. The surface temperature falls below about 1,000 Kelvin. Visible light effectively disappears. The object still radiates, every warm body radiates, but it does so in the infrared, beyond what the human eye can detect. To any ordinary telescope working in visible light, the object is no longer there. To an infrared telescope, it is a small, dim, slightly warm point. The cooling has slowed dramatically by this stage, because a cooler body radiates much less strongly than a hot one. What took millions of years in the early phases now takes hundreds of millions, then billions. The pace slackens. The descent flattens. The fifth stage is the very long thermal tail. The surface temperature drops below a few hundred Kelvin, then below 100, then below 10, then below 1. The object is now radiating only into the microwave and far infrared bands. The cooling becomes nearly imperceptible from one age of the universe to the next. The crystallization is fully complete, and the latent heat that crystallization released is mostly already gone. The white dwarf is now in its final long descent toward the temperature of the cosmic background. It is essentially a black dwarf already, in the sense that nothing visible is happening anywhere on it, but it is still slightly warmer than the universe around it, and so, formally, it is not yet a black dwarf. The sixth stage is the arrival. The surface temperature of the cooled remnant finally matches the temperature of the cosmic microwave background. The object is now, by definition, in thermal equilibrium with its surroundings. It is no longer giving off net radiation. It is no longer losing heat. It has reached the temperature the universe set for it. This is the black dwarf. This is the end of the long road. The cooling is complete. You might notice that the road we just walked spans an inconceivable amount of time. The first few stages take hundreds of millions to billions of years. The middle stages take many billions. The final stages take far, far longer than the current age of the universe. Bringing the surface temperature of a white dwarf from, say, 3,000 Kelvin down to 100 takes longer than the entire history of the cosmos so far. Bringing it from 100 down to a few takes longer still. The full road, from the hottest fresh white dwarf to the fully cold black dwarf, takes about 1 quadrillion years, a number written as 10, with 15 zeros after it. To put that next to the present age of the universe, you can imagine the cosmos as a single early morning hour in a day that lasts roughly 100,000 hours. We live in the first hour. The black dwarf is the kind of object that becomes ordinary somewhere around the middle of the day, long after lunch, in a slow and uneventful afternoon that has not yet begun. That comparison is, in a real sense, what you are listening to. The cosmos is unfinished. The patient end states are still in the future. The first black dwarves are still ahead. And the road that leads to them is being walked, very slowly, by every white dwarf, in every galaxy, in the observable universe, right now, in this exact moment, as you settle into wherever you are. There is another small fact about this road that is worth holding. A white dwarf cools because it radiates heat into the surrounding sky. But the surrounding sky is not perfectly cold. The cosmic microwave background sits at about 3 Kelvin in our era. so a white dwarf can only cool as far as that background allows. If the universe stopped expanding tonight, the background temperature would not change, and the coolest a white dwarf could ever reach would be 3 Kelvin, still slightly warm by the standards of the very deep future. But the universe is expanding, and as it expands, the cosmic microwave background cools. The background was once thousands of Kelvin in the early universe. It is now 3 Kelvin. In the deep future, it will be far below 1 Kelvin, then far below a millionth of a Kelvin, and so on, indefinitely. The colder the background, the lower the final equilibrium temperature a white dwarf can reach. So the destination of the cooling road actually moves over time. The black dwarf of a quadrillion years from now will be warmer than the black dwarf of a quintillion years from now, which will be warmer than the black dwarf of even further out. The cosmos cools alongside the dwarves, and they always have just a little farther to fall. This is one of the small, beautiful subtleties of the subject. A black dwarf is not a single fixed temperature. It is a moving target. The white dwarf is always chasing the background, and the background is always slipping a little farther away. Over the deep future, the two converge, but they do so on a timescale so long that even the word long stops feeling adequate. You might be drifting now, listening to this. That is appropriate. The cooling road is exactly the kind of subject that is best taken slowly. There is nothing on it that needs your attention. Nothing that demands a response. Nothing that asks anything of you. The white dwarves of the universe are cooling whether you are awake or asleep, whether you are aware of them or not, and they will continue to cool for as long after this night as anyone is willing to imagine. There is one more soft motif worth naming as we leave this part. The cooling sequence is the universe's slowest single process. The expansion of space is slow. The motion of galaxies is slow. The cooling of a planet is slow. But the cooling of a white dwarf into a black dwarf takes longer than all of those things combined by enormous margins. It is the slowest thing the universe knows how to do at the scale of a single object. And in that slowness, there is a kind of permission. If the universe can take 100,000 times its own current age to finish a single cooling, then perhaps you can let your shoulders soften now and trust that the unfinished things in your own life have all the time they need. It can help to slow down even further on the cooling road itself, because the rhythm of it is part of what makes it restful. The cooling of a white dwarf is not steady in the way a candle is steady. It is not steady in the way a campfire is steady. It is steady in the much gentler, much slower way that geological processes are steady. The cooling proceeds at a rate that no human observer would ever notice. From one human lifetime to the next, a white dwarf does not detectably change. From one century to the next, the change is still beneath any reasonable measurement. Even from one millennium to the next, the temperature drops by amounts that are extremely difficult to measure. The cooling is, in human scale terms, almost stationary. But over millions of years, the change accumulates. The hottest white dwarves slowly drift toward cooler classifications. The cooler ones drift further still. Over billions of years, the population of white dwarves in our galaxy shifts toward the cooler end of the temperature range. The very oldest white dwarves, those that formed in the earliest generations of sun-like stars, are now the coolest objects in the white dwarf population. They are not yet black dwarves. They are not even close to being black dwarves. But they are noticeably cooler than the younger white dwarves around them, and that coolness is the visible evidence of the long road in motion. It is worth picturing that population for a moment. The Milky Way is thought to contain something like 10 billion white dwarfs at any given time. Some are very young, freshly formed from sun-like stars that have just completed their lives. Some are intermediate-aged, cooling through the yellow and orange phases. Some are older still, cooling through the red phases. And some are the most ancient of all, descended from the very first sun-like stars to die, now slowly approaching the dim red end of the cooling range. The full population spans the entire spectrum of cooling stages, with younger generations continuously joining at the hot end and older generations gradually drifting toward the cool end. It is, in a sense, a cosmic-scale slow conveyor belt, with white dwarves entering from one side and slowly making their way across. In our local neighborhood of the galaxy, there are dozens of known white dwarves close enough to be studied in detail. Some are the cooling remnants of stars that lived and died within the past 100 million years. Some are the remnants of stars that died several billion years ago. The temperature range across the local sample is broad. Every star is on the same cooling curve, just at different points along it. Together, they form a snapshot of the cooling process in action, the universe's slow conveyor belt, captured in a single moment of time. The slow conveyor belt itself extends backward through the entire history of the galaxy. The first white dwarfs in the Milky Way formed something like 12 or 13 billion years ago, in the very earliest generations of sun-like stars. They have been cooling for almost the entire history of the cosmos. Their current surface temperatures sit somewhere around 3000 Kelvin, give or take. That is still extraordinarily warm by black dwarf standards. The remaining cooling road is far longer than the cooling that has already been done. The oldest white dwarfs in the Milky Way have, in a real sense, only just begun their journey. This is one of the small ways the universe softens its own enormous timescales. The cooling of a white dwarf, taken from start to finish, is a span of about 1 quadrillion years. The portion that has already been completed by the oldest known white dwarfs, about 13 billion years, is roughly 1 part in 100,000 of that total. The fraction of the cooling road that is behind any cooling white dwarf in the universe right now is essentially negligible. The road is, in every meaningful sense, all still ahead. Even the oldest white dwarfs in our galaxy are, for all practical purposes, at the very beginning of their cooling. Let your shoulders soften with that thought. The cosmic conveyor belt is moving, but it is moving so slowly that what looks like an old white dwarf to us is, on the cosmic scale cooling curve, still essentially fresh. The universe is, in this very specific sense, building its black dwarf population from scratch, and it has done almost none of the building yet. The conveyor belt has a long way to run. There is no part of this process that needs you to attend to it. The cosmos is doing its slow work without any need for assistance, observation, or hurry. To understand when the first black dwarfs will appear, it helps to step back and look at the very long shape of cosmic history. Cosmologists who study the deep future of the universe have proposed a simple way of organizing the unimaginable spans of time ahead. They divide the future into a small number of long, named eras. Each one is far longer than the one before. The black dwarf belongs to one of those eras. It is worth walking through them, gently, so that the time scale comes into a kind of soft focus. The first era, looking backward, is the primordial era. It is the brief stretch of time between the Big Bang and the formation of the first stars. It lasted only a few 100 million years. The universe was hot and dense and almost featureless. There were no galaxies. There were no stars. There were no planets. there was only a slowly cooling fog of hydrogen and helium, gradually clumping under gravity into the structures that would eventually give birth to the first generations of stars. This era is the prologue of everything that follows. The second era is the stelliferous era, the era of stars. It begins with the lighting of the first stars and continues for an enormous stretch of cosmic time. The accepted estimate is that the stelliferous era lasts from a few 100 million years after the Big Bang until somewhere around 100 trillion years from now, give or take. During this era, galaxies form and rotate. Stars are born from gas clouds, burn hydrogen, age, die, scatter heavy elements into space, and contribute to the next generation. The night sky is full of starlight. Planets form. Moons form. Worlds rise and fall. Living things, where they exist, look up and see a richly populated sky. We live in the stelliferous era. In fact, we live near the very beginning of it. The universe is about 13.8 billion years old. The stelliferous era is roughly 100 trillion years long. We are, in the most generous reading of cosmic time, in the first 14,000th of it. The cosmic morning, in other words, has barely begun. The vast majority of starlight that will ever exist in this universe is in front of us, not behind us. The stars you can see tonight are some of the very earliest stars ever to give light. The galaxies we know are some of the youngest galaxies that will ever exist. Everything we are accustomed to about the night sky is, in cosmic terms, brand new. The third era is the degenerate era. It begins, roughly, when star formation grinds to a halt. The gas needed to make new stars is steadily locked into existing stars, blown out of galaxies by feedback processes, or eventually consumed entirely. The youngest red dwarfs will outlive every other kind of star, but eventually even they exhaust their hydrogen and quietly fade. After the last red dwarfs have settled into helium-white dwarfs and gone dark, the cosmos enters the long age of stellar remnants. The degenerate era is the age of brown dwarfs drifting cold in former star-forming regions, of white dwarfs slowly cooling into black dwarfs, of neutron stars cooling toward equilibrium with their surroundings, and of black holes growing slowly through occasional accretion. The degenerate era is where the first black dwarfs arrive. It begins around 100 trillion years from now, and runs for somewhere on the order of 10 to the 37th years, a number written as 10 with 37 zeros after it. The first black dwarfs appear within this era, when the oldest white dwarfs, the ones formed from the very first sun-like stars in the early universe, finally finish their cooling journey. From then on, the black dwarf population grows steadily, as later and later white dwarfs cross the same threshold. Eventually, the universe is, in its most populous structure, a vast scatter of black dwarfs drifting through dim and dispersing galaxies. The fourth era is the black hole era. It begins when even the longest-lived stellar remnants have either decayed or been absorbed into black holes. If protons decay, and we will discuss this carefully in a later part of this walk, then ordinary matter, including black dwarfs, gradually dissolves over an unimaginable stretch of time, leaving behind black holes as the dominant structures of the cosmos. The black hole era is the age of the universe in which everything that is not a black hole has, more or less, vanished. The era runs from somewhere around 10 to the 37th years to around 10 to the 100th years. The latter number 10, with 100 zeros after it, is so large that it has its own name in popular mathematics. It is called a googol. The black hole era is, in this sense, the googol year age of the universe. The fifth era is the dark era. It begins after even the largest black holes have evaporated through a slow quantum process that physicists call Hawking radiation. The smallest black holes evaporate first. The largest take by far the longest. After every black hole has finally finished its long evaporation, the cosmos is left with nothing more than a thin, diffuse soup of low-energy photons, neutrinos, and stray particles, drifting in an enormous and almost perfectly empty space. The temperature of that soup is barely above absolute zero. Nothing happens in the dark era, in any meaningful sense. There are no stars. There are no planets. There are no remnants. There is only the gentle drift of particles in the cold. The dark era has no defined upper limit. It simply continues. The universe, in this picture, goes on existing forever in a state of essentially perfect quiet. There may be very, very rare quantum events, fluctuations in the vacuum, brief and almost meaningless local arrangements, but for all practical purposes, the universe in the dark era is at rest. It has finished doing the kinds of things universes do. Now, you can step back from this five-era picture and notice the shape of it. The primordial era is brief. The stelliferous era is long, but bounded about 100 trillion years. The degenerate era is far longer, about 10 to the 37th years. The black hole era is far, far longer than that, about 10 to the 100th years. And the dark era is, in principle, unbounded. Each era is much longer than the sum of all earlier eras. The shape of cosmic time is not symmetric. It is heavily weighted toward the future. The present moment, with its glowing stars and its forming planets and its life-bearing worlds, sits at the very beginning of a story whose later chapters dwarf it in every dimension. The black dwarf lives in the second of these eras. The degenerate era is its home. It is the object that fills the long quiet between the end of stars and the beginning of the black hole-dominated cosmos. It is the universe's patient ending, and the universe is taking its time getting there. You might find this picture, if you let yourself sit with it for a moment, almost paradoxically restful. The cosmos is not running out of time. The cosmos has so much time that the present era, with all its activity and brightness and warmth, is only a tiny bright morning before an enormous afternoon and a still larger evening. We live in the beginning. The patient endings are real and inevitable, but they are not happening yet. The first black dwarves are not even close to arriving. The degenerate era is not even close to beginning. The black hole era is so far away that the very concept of distance starts to feel inadequate to the time involved. It can help to put it another way. If you wanted to compress the entire five-era timeline of the universe into a single day, the primordial era would last about 1/1000th of a second. The stelliferous era would last for about the first second of that day. The degenerate era would last for the next several thousand years of that compressed day. The black hole era would last for several trillion compressed years after that. And the dark era would last forever. The very first black dwarves would appear roughly 1 second into that compressed day. We live in the first millionth of that first second. We are, by any reasonable measure, in the freshest dawn of cosmic history. It is easy to think of the future of the universe as something dramatic, a fate, an ending, a catastrophe. That is the language often used. But the actual shape of the future is gentle. The degenerate era is not violent. It is simply quiet. The black hole era is not violent. It is simply emptier. The dark era is not violent. It is simply still. The universe does not crash. It does not break. It does not fail. It simply, slowly, takes its time. And the black dwarf is what fills that taking. It is the patient object that arrives long after the stars have finished, and that persists long after the galaxies have dispersed, and that does not ask anything of anyone. It is one of the universe's last, quietest expressions of structure. A small, dense, cold, perfectly stable lump of carbon and oxygen drifting through a sky that has long since lost its light. That is what the road of the white dwarves is heading toward. That is the destination of every sun-like star you can see tonight. And the universe, in its enormous patience, is taking many trillions of years to get there. Let your breathing slow with that thought. There is no part of this story that needs you to hurry. The eras themselves are not hurrying. The cosmos has, in the most literal possible sense, all the time it needs. And it has just begun. It can help to spend a little more time inside the degenerate era specifically, because it is the era in which the black dwarf is the natural inhabitant. The degenerate era is named for the kind of matter that fills it, degenerate matter, the same electron-degenerate matter that fills the interior of a white dwarf. By the time the degenerate era is fully underway, the dominant objects in the universe are the cooled remnants of stars that lived during the stelliferous era. Brown dwarfs, white dwarfs, slowly cooling into black dwarfs, the cores of red dwarfs that have finally exhausted their fuel and become helium white dwarfs themselves, neutron stars cooling toward thermal equilibrium with the very cold sky around them, and stellar mass black holes left over from massive star supernovae. All of these are the residents of the degenerate era. The era is long. Even by cosmic standards, it is long. It runs for somewhere on the order of 10 to the 37th years, which is to say roughly 27 orders of magnitude longer than the present age of the universe. Over that immense stretch of time, the degenerate era is the period in which most of cosmic history, by simple duration, takes place. Far more cosmic time elapses during the degenerate era than during everything that has come before it combined. If you imagine cosmic history as a long thread laid out on a table, almost all of it is the degenerate era. The stelliferous era, the era we now inhabit, is a small bright spot near one end. The conditions within the degenerate era change slowly across that span. Early in the era, the universe still resembles, in broad outlines, the universe we know. Galaxies still exist, although they no longer form new stars. The remnants of old stars drift through them. The cosmic microwave background is still detectable, though much cooler than it is today. The Milky Way's descendant, whatever it has become after merging with Andromeda and other local group neighbors, is still recognizable as a structure. Across hundreds of trillions of years, that recognizable structure gradually dissolves. Stellar encounters scatter most of the cooled remnants outward. The central black hole absorbs a fraction. The galaxy, as a coherent structure, slowly evaporates. By the middle of the degenerate era, the universe is a vast scatter of small, cooled bodies, drifting through enormous and almost perfectly empty volumes of space. The galaxies are gone, in the sense that the structures that once held stars together no longer exist. What remains is a population of black dwarfs, neutron stars, and black holes, distributed sparsely across an expanded cosmos. The distances between objects are unimaginable. A typical black dwarf in this era might have its nearest neighbor at a distance of many millions of light years. The intergalactic spaces of our era have, by the middle of the degenerate era, become the typical conditions everywhere. Late in the degenerate era, if protons decay, the matter inside black dwarfs and neutron stars begins to slowly dissolve. The cooled remnants gradually fade into thin clouds of lighter particles and radiation. The dominant objects of the universe shift over enormous stretches of time, from cooled stellar remnants to black holes. By the very end of the degenerate era, only the black holes remain. The transition into the black hole era is not a sharp event. It is, again, the gradual completion of a process that has been underway for a very long time. This is the cosmic context in which the black dwarf is at home. It is the patient inhabitant of a long, quiet era. It is the most numerous large object in that era. It is the cosmos's longest-running quiet citizen. And it spends almost the entire duration of that era, many tens of orders of magnitude longer than the present age of the universe, simply existing, slowly cooling, slowly settling, slowly dissolving if protons decay, slowly persisting if they do not. Let your eyes settle and your breathing slow with that thought. The black dwarf does not have a brief existence. It is not a flicker. It is one of the most permanent things the universe knows how to make. Its lifespan, in any reasonable accounting, is longer than the entire current age of the universe by many enormous factors. It is the patient evening of a sun-like star, and that evening is long, much, much, much longer than the bright morning we currently inhabit. The cosmos has a great deal of evening ahead of it. The black dwarf is the gentle company we will not be there to keep, but which the universe is preparing for itself, nonetheless. There is something gentle about telling this story through the Sunday. The sun is not abstract. It is the star that holds Earth in orbit, that lights the day, that has warmed every living thing in the only place we know life exists. And the sun is, by every measure we have, an ordinary sun-like star. Ordinary stars become white dwarfs. White dwarfs become black dwarfs. So the sun, in the very long view, is itself on the road we have been describing. Tonight, you can let your attention settle on what that road looks like for our own star, not as a fearful event, but as the calm sequence of stages that lie ahead of it across timescales so vast that they make the present feel almost cozy by comparison. The sun is, at the moment, about 4.5 billion years old. It has burned hydrogen in its core for that entire time and is roughly halfway through the main sequence phase of its life. It has another 5 billion years or so of hydrogen burning ahead of it, give or take. During those 5 billion years, it will grow gradually brighter and slightly larger, as main sequence stars do, but it will remain recognizably itself. It will keep doing what it has been doing, quietly converting hydrogen into helium in its very hot core, leaking that energy outward as light and heat. After those 5 billion years are up, the sun will run low on hydrogen at its center. The core will contract slightly, growing hotter, and a shell of hydrogen around the contracted core will begin to fuse. The outer layers of the sun will respond to this change by expanding dramatically. The sun will leave the main sequence and become a red giant. Its surface will swell outward by a factor of dozens, then hundreds. Its color will deepen toward orange and red. Its outer layers, although enormously distended, will be cooler at the surface than the present Sunday. In that swelling, the sun will engulf Mercury. It will engulf Venus. The fate of Earth is less certain. The sun's swelling outer envelope may or may not reach Earth's orbit. In some models, Earth is engulfed and gradually evaporates inside the giant's tenuous outer layers. In others, the sun's mass loss during this period lifts Earth's orbit outward enough that Earth survives, but as a charred, atmosphere-stripped husk, orbiting in a much closer relationship with a star that has fundamentally changed. Either way, the world we know does not last as a place. Long before the red giant phase, in fact, the sun's gradual brightening will have rendered Earth too hot for liquid water on its surface. The familiar Earth is a temporary arrangement. After the red giant phase, the sun's core will undergo its own changes. Helium fusion will ignite in the central regions. The sun will become temporarily smaller and hotter again. It will spend a brief stretch, only 100 million years or so, burning helium in its core, producing carbon and a smaller amount of oxygen. When the helium runs out, the sun will go through a second giant phase, brighter and even more bloated than the first. Throughout these later phases, the sun's outer layers will become increasingly unstable. They will pulsate. They will lose mass to space at growing rates. The wind of material flowing outward from the surface of an old red giant is gentle compared to a stellar explosion, but over time it strips away a significant fraction of the star's total mass. Eventually, the sun's outer layers will be lifted away entirely. The thin, expanding shell of gas that drifts outward at this point will be illuminated from within by the sun's exposed core. For a brief stretch of time, only a few tens of thousands of years, the sun will produce a soft, glowing planetary nebula, a delicate shell of gas around a small, brilliant, freshly exposed white dwarf at the center. The planetary nebula is one of the loveliest things a sun-like star can do. It is a slow exhalation of light. It is the star saying goodbye, very gently, to the matter that once made up its outer layers. After the planetary nebula has drifted away and dispersed, what is left is the sun's exposed core, a fresh white dwarf, roughly half the sun's present mass, packed into a sphere about the size of the Earth. This is the moment when the sun enters the long road we have been describing. The cooling begins. The white dwarf is extraordinarily hot at first, a tiny, brilliant point in a sky that has just lost its planetary nebula. From that moment forward, the only thing it will do is cool. The sun, in its white dwarf phase, will spend hundreds of millions of years in the hot yellow-white range. It will then spend billions of years in the yellow, then orange, then red phases. Crystallization will eventually begin in its core, releasing a small amount of latent heat that gently slows the cooling. The sun's white dwarf self will dim through the red phase, into the infrared, into the far infrared, into the microwave. It will become invisible to any imagined ordinary telescope. It will continue to cool for what is, in our human terms, an unimaginable stretch of time. Eventually, after a span of about 1 quadrillion years, give or take, the sun's white dwarf self will finish its cooling. The surface temperature will have reached the temperature of the cosmos around it, whatever that is at the time. By then, the cosmic microwave background will have cooled to far below a Kelvin, and the sun's final equilibrium will be at that very low temperature. At that moment, the sun will, by definition, be a black dwarf. It will be the patient ending of the star you watch rise tomorrow. The transition will not be marked by any dramatic event. It will simply be the moment when the cooling stops. You might be wondering, listening to this, what happens to Earth and the other planets in all of that time? The short answer is that, on the longest timescales, they probably do not stay with the Sunday. The sun's mass loss during the giant phases will loosen the orbits of all its remaining planets. The outer planets, especially the gas and ice giants, will likely survive the giant phase intact, but will end up in much more distant orbits than they have now. Over the much longer span of the white dwarf cooling, occasional encounters with passing stars will gradually perturb these orbits. Eventually, On timescales of trillions of years, most of the surviving planets will be scattered away into interstellar space. The Sun, in its eventual black dwarf phase, will most likely drift alone. There is a quietness to that final picture that is hard to overstate. The Sun, having lived its full main sequence life, having shed its outer layers, having cooled through every color of starlight, finally settles into a small, dark, crystalline relic, no larger than a planet, drifting through a galaxy that no longer holds it. Most of its original family has scattered. Its light is gone. Its warmth is gone. Only the matter remains, in the shape of a quiet, planet-sized body that no eye will ever see. But notice that the matter remains. That is one of the gentle facts about this whole story. The atoms of the Sun do not vanish. The carbon and oxygen produced in its core during the helium-burning phase are exactly the carbon and oxygen that make up the body of the future black dwarf. Those atoms are conserved. They are still themselves. The black dwarf is, in a real sense, the Sun saved in a different form, its core preserved, frozen, structurally complete, persisting in the cold for almost forever. It is also worth saying that none of this is happening tonight. The Sun has billions of years of ordinary main sequence life ahead of it. The red giant phase is more than 5 billion years away. The white dwarf phase is even further. The cooling road to the black dwarf is many quadrillions of years long after that. The story of the Sun's ending is real, and it is inevitable, and it is also so far away in time that it cannot disturb anything about the present. In fact, one of the gentler ways to hold this whole subject is to notice that the Sun's eventual fate is itself a measure of how patient the cosmos is willing to be with its own contents. The Sun has been here for 4.5 billion years and has another 5 billion to go in its ordinary form. After that, it will spend roughly 1 billion more years going through giant phases. Then it will spend the entirety of the remaining cosmic time we have been discussing the entire long white dwarf cooling, all the way down to the black dwarf state in a single, steady, gradual descent. There will be no event, no dramatic moment, no sudden shift. Only the cooling. The Sun, like every other sun-like star, gets a very long, very slow, very quiet ending. There is a soft thread that has appeared in earlier walks through this kind of subject, the recurring soft idea that the most interesting events in the universe often unfold without anyone watching them, and that this absence of witness is not a tragedy but a kind of integrity. The Sun's eventual journey to a black dwarf state belongs to that idea. There may be no one alive to see the planetary nebula. There may be no one to see the white dwarf cool. There will almost certainly be no one to mark the moment when the cooling ends and the black dwarf phase begins. The Sun will do all of these things by itself. The matter does not require an audience. The cosmos does not require an audience. The cooling proceeds because the laws of thermodynamics ask it to, and that is enough. You might let your eyes settle and your breathing soften with that thought. The Sun will become a black dwarf. The road is enormous. The road is gentle. The road has already, in a sense, begun. Every photon the Sun has ever radiated has been a small leak from a finite store of energy, and the long sequence of leaks that follows the end of fusion is the cooling we have just described. The road is in motion. The destination is real. And you are very, very early on the road. Tonight, the Sun is still here, doing what it has been doing for almost 5 billion years. You can let that too be a kind of comfort. It can help, gently, to dwell a little longer on what happens to the inner solar system in the Sun's long ending, because the details are themselves part of the rest. Mercury and Venus, the two innermost rocky planets, are almost certainly engulfed during the Sun's red giant phase. The Sun's outer envelope will swell to a radius that exceeds the orbits of both planets, and the friction with the bloated stellar atmosphere will slow both of them on a timescale of mere centuries. They will spiral inward and be absorbed into the Sun's outer layers, contributing a small amount of their material to the eventual planetary nebula that the Sun will shed. The two planets, as places, will not exist after that. Their atoms, however, will be there scattered through the expanding gas of the planetary nebula, eventually drifting outward into interstellar space, eventually mixed with the gas of the next generation of stars. Earth's fate is, as we mentioned, more uncertain. The competing influences are the Sun's expanding outer envelope, which would engulf Earth if Earth stays in its current orbit, and the Sun's mass loss during the giant phase, which tends to push the orbits of remaining planets outward. The two effects are roughly comparable in magnitude. Some careful calculations suggest Earth is engulfed. Others suggest Earth is left in a slightly wider orbit around the post-giant Sun, charred but intact. Either way, Earth as a habitable place is finished long before the engulfment question becomes relevant. The Sun's slow brightening over the next billion years or so will cause Earth's oceans to evaporate, leaving the planet dry and far too hot for any surface life. The familiar Earth, the one with oceans, with weather, with plants and animals, is a temporary phenomenon, with a remaining lifespan measured in hundreds of millions of years rather than billions. The outer planets fare much better. Jupiter, Saturn, Uranus, and Neptune are far enough from the Sun that they will not be engulfed during the giant phase. They may, in fact, find themselves in somewhat warmer surroundings. During the height of the Sun's red giant brightness, Jupiter might briefly experience temperatures comparable to those of present-day Earth, and the icy moons of the outer planets might experience a brief, geologically transient period of liquid surface conditions. But these warm phases are brief and end with the planetary nebula's exhalation. After the Sun becomes a white dwarf and begins its long cooling, the outer planets settle into very cold, dim, slowly fading orbits around a small, dense, gradually cooling stellar remnant. The icy moons of the outer planets will keep their internal warmth for a while. The moons that have subsurface oceans today, Europa, Enceladus, perhaps Titan and Ganymede, will continue to have those oceans for some time after the Sun's death, because the warmth comes from internal heat sources, radioactive decay, tidal flexing, rather than from sunlight. Eventually, however, the internal heat sources will exhaust themselves. The oceans will freeze through. The moons will become geologically inert, frozen all the way through, dim and quiet companions to dim and quiet outer planets, all of them orbiting a small white dwarf that is itself slowly cooling toward eventual black dwarf state. The fate of the planetary orbits themselves, over the very long term, is one of slow randomization. Encounters with passing stars over hundreds of billions of years will gradually perturb the orbits of the surviving planets. Some will be ejected from the system entirely, becoming rogue planets adrift in interstellar space. Some will fall into more eccentric orbits around the cooling Sunday. Over a sufficiently long timescale measured in trillions of years, the typical fate is ejection. The black dwarf Sun, eventually, is most likely solitary. But most likely is not, certainly. It is entirely possible that one or two of the outer planets remain bound to the cooling Sun, even on cosmic timescales. The Sun might still have a quiet companion when it becomes a black dwarf, a dim, cold Jupiter or Saturn, drifting in a slow, distant orbit around an even dimmer, colder stellar remnant. The pair would be invisible by any ordinary standard. They would drift together through whatever galactic environment the deep future provides. They would be, in a quiet way, one of the small leftover families of the early cosmos, a sun-like star system that did not entirely dissolve. You might find that image gentle. The sun and one or two of its outer companions persisting together through trillions of years, drifting silently through a sky that no longer has visible stars in it. The matter of our solar system would, in this picture, still be a family, still in slow gravitational conversation, still recognizable as the cooled-down version of the system we inhabit today. The arrangement would be quieter than any present sky. The structure would be smaller and dimmer than the present solar system. But it would, in some real sense, still be the same system. The cosmos sometimes lets these arrangements last for very long indeed. Let your breathing soften with that thought. The sun's long road home does not necessarily strand it alone. The deep future is full of patient endings, and some of those endings include patient companionship. The cosmos, in its very long view, is not as lonely as it might first appear. A black dwarf, by definition, gives off essentially no visible light. That fact alone makes it one of the strangest possible objects to imagine observing. Almost everything astronomers have learned about the universe has been learned by looking at light. The colors of stars tell us their temperatures. The spectra of galaxies tell us their compositions and motions. The brightnesses of distant supernovae tell us the geometry of cosmic expansion. The light from a black dwarf, however, is so weak that the ordinary tools of astronomy would never see it. So how, in principle, would anyone ever know one was there? The answer, gently, is gravity. A black dwarf still has mass. Mass still curves spacetime. And in a universe of dim and cold objects, gravity remains a reliable signal, perhaps the only fully reliable one. The methods that would be used to detect a black dwarf in some hypothetical far future astronomy all rely on gravity. There are a few of them worth walking through. The first is gravitational microlensing. This is a real technique that astronomers use today to find dim or invisible objects. The idea is straightforward. When a massive object passes precisely in front of a more distant light source, a background star, a distant galaxy, the gravity of the foreground object bends the light from the background source and briefly focuses it. The background source temporarily appears brighter, then dimmer again as the alignment slips. The brightening curve is symmetric and has a very particular shape that depends on the mass of the foreground object and the geometry of the encounter. Microlensing is, in this sense, an ancient and gentle method of looking at the dark. Today, microlensing surveys find rogue planets, brown dwarves, and stellar mass black holes. In a far future cosmos with significant black dwarf populations, microlensing would also reveal them. A black dwarf passing in front of a distant background source would produce a microlensing brightening of exactly the shape predicted for a sun-mass compact object. If one were ever found, the detection would not be of the object itself, but of the brief, gentle distortion of light from something farther away. The second method involves binary companions. Many stars in our galaxy live in binary or multiple systems, two stars orbiting a common center of mass, each pulling the other. If one of those stars dies and becomes a white dwarf and eventually a black dwarf, the system is still gravitationally intact. The black dwarf is still there, still pulling its companion in a small periodic dance around the system's center of mass. If the companion is still glowing, perhaps it is a red dwarf with a much longer lifespan, or a more massive star still in its main sequence phase. or another stellar remnant of a different kind, then careful measurements of the companion's motion would reveal the invisible partner. The companion's wobble would betray the black dwarf's presence. In the deep future of the universe, when most ordinary stars have died but red dwarfs are still slowly burning, such binary systems would be one of the cleaner ways to identify black dwarfs. The bright companion would do the work of revealing the dark one. The geometry would be unmistakable, a small, gentle, repeating motion of the visible star, exactly the kind of motion a hidden partner with a star's worth of mass would produce. The third method involves the faint, residual radiation that a black dwarf does give off. We said earlier that a black dwarf is not perfectly cold. Its surface temperature, by definition, matches the temperature of the cosmic microwave background. But the background is itself cooling over time, and in the very deep future, it will be far colder than any black dwarf can be, because each black dwarf has some small internal heat source that prevents it from reaching the limit. There is the latent heat from crystallization, slowly leaking out. There is, possibly, a small contribution from the very slow decay of protons, if protons decay at all. Whatever the source, a black dwarf will radiate weakly in the microwave and far infrared bands, slightly warmer than the cold sky around it. In a future cosmos cold enough for that contrast to stand out, when the cosmic background has dropped to, say, a millionth of a Kelvin, a black dwarf at a few Kelvin would shine, in its quiet way, as one of the relatively warm objects in the universe. Far future astronomy with instruments designed to detect very faint infrared and microwave sources against an extraordinarily cold sky could, in principle, see them. The detections would not look like stars. They would look like small, dim, slightly warm points against an otherwise frigid background. They would be visible only by their very gentle warmth. The fourth method is more subtle, and it is one of the few ways that present-day astronomy can actually probe the eventual existence of black dwarfs. Even today, the cooling curves of the oldest known white dwarfs give hints about the late stages of stellar cooling. By measuring how many white dwarfs of each temperature, we observe building up what astronomers call a luminosity function, and by comparing those measurements to theoretical predictions, scientists can test the physics of the very late cooling stages. A small bump in the luminosity function at a particular temperature corresponds to the predicted slowing caused by crystallization. A different shape might suggest something else. These detailed studies of present-day white dwarfs give us a way of testing the eventual road to black dwarfs without ever seeing one. It is a quiet kind of science. Astronomers cannot point a telescope at a black dwarf because none exist. But they can use the white dwarfs that do exist to test the physics of cooling and to confirm, indirectly, that the road we have been describing is real. Every present-day white dwarf with a slightly flattened cooling curve at a particular temperature is itself a small piece of evidence that the long road to a black dwarf is indeed what physics insists it will be. You might ask, gently, why none of these methods have ever found a black dwarf. The answer is the entire content of this video. There are none to find. The microlensing surveys do not detect what does not exist. The binary surveys do not detect what has not formed. The luminosity functions of the oldest known white dwarfs match a population that is still squarely in the cooling phase, with surface temperatures of a few thousand Kelvin, far warmer than any black dwarf could be. The non-detection of black dwarfs is not a failure of instruments. It is a confirmation of cosmic age. The universe is too young to have made any. This is an unusual scientific situation, and it has a soft elegance to it. The non-existence of black dwarfs is itself a finding. It tells us, very precisely where we are in cosmic time. It tells us that the present universe is still on the early side of its long road. It tells us that the patient endings are real, predicted by physics, locked into the future, but not yet here. There is, in this absence, a kind of confirmation that the model we have been walking through is correct. The universe is still building the population. The first arrivals have not happened. There is one more idea worth mentioning, because it is unexpectedly beautiful. In the very deep future, when black dwarves are common, the methods of observing them might themselves be carried out by black dwarf-era civilizations or instruments, if such things existed. We have no way of knowing whether intelligence in any form would persist into the degenerate era. The conditions for life as we know it are unlikely to last that long. But the possibility is there, in principle, that some patient form of observation could persist, and that the methods we have just described would be the actual tools used in some distant deep future to count and study the very objects we are imagining tonight. Every black dwarf would have a place on some long catalogue. Every microlensing event would be timed and recorded. Every binary system with a hidden partner would be added to a quiet, patient census of cold things in a cold sky. That is, in some sense, the gentlest possible image of late cosmic astronomy. Not the fevered observation of bright, fleeting events, but the slow, careful counting of small, dim, quietly warm bodies drifting through an empty universe. It is the kind of astronomy that would feel, more than anything, like an ongoing meditation. There would be very little new. There would be only the slow population of catalogues and the gentle confirmation that the cosmos was, on its longest timescales, finishing its thought. Tonight, we are very, very far from that kind of astronomy. The universe is bright. The galaxies are full of stars. Black dwarves are still a future class. The methods we have just walked through are the methods that would eventually find them. For now, the methods can be tested and developed on white dwarves, on rogue planets, on brown dwarves, on dim stellar remnants of various kinds. The tools are in place. The targets, in the form of black dwarves, are not. You can let yourself rest in that contrast for a moment. We live in a universe where black dwarves are predicted but absent. The tools that would see them already exist in rudimentary form. The objects that they will eventually observe are still being made, one by one, in the slow cooling of the white dwarves around us. The universe is, gently, both ready and not ready. Ready for the methods, not yet ready for the objects. It is one of the many small, quiet mismatches that make the deep future feel close enough to imagine, even though it is, in every literal sense, very far away. And the absence of black dwarves tonight is not a problem. It is not a gap. It is not a question waiting to be answered. It is simply where the cosmos is in its long unfolding. The universe is right on schedule. The black dwarfs will come. There is no rush. It can help to think a little more carefully about what gravitational microlensing actually looks like, because the technique is itself quietly beautiful. When a foreground object, say, a future black dwarf, passes precisely in front of a more distant point of light, its gravity bends the light from that distant source. The bending produces, in effect, a temporary lens. The distant point of light is briefly magnified, briefly brightened, briefly multiplied into a small cluster of images that the imperfect resolution of any practical telescope blurs back into a single point. The whole event is gentle. There is no flash. There is no sudden change. There is only a slow rise in apparent brightness, a peak, and a slow descent back to normal. The full encounter typically lasts days to months, depending on the mass of the foreground object and the geometry of the alignment. Microlensing is, in a real sense, the universe's way of letting us see things that have no light of their own. A rogue planet, drifting through interstellar space, can be detected only by the gentle brightening of a background star when the planet happens to pass in front of it. A stellar mass black hole, far too dark to be seen directly, betrays its presence in the same way. A black dwarf, in a far future cosmos, would do the same. The technique works because gravity is universal. It applies to every object with mass, regardless of whether that object glows. In a sky full of cold and silent things, gravity remains the one signal that always works. The future astronomy of black dwarves, if it ever happens, would be largely a microlensing astronomy. Surveys would scan large portions of the sky, monitoring vast numbers of background light sources for the characteristic brightening that signals a foreground gravitational encounter. Each detection would be a one-time event, never to be repeated, because the geometry of any given alignment is unique. The catalogue would build slowly over millions or billions of years of patient observation. Each new black dwarf would be added to the list by virtue of its single, brief, gentle distortion of distant light. The pace of the survey would match the pace of the cosmos itself. Unhurried, careful, deeply patient. The binary companion method has its own quiet beauty. In a cosmos where most stars have died, but some still burn, a black dwarf in a binary system reveals itself through the motion of its visible partner. The partner traces a small ellipse around the system's center of mass. The size and period of the ellipse encode the mass of the invisible companion. The technique is the same one used today to find dim brown dwarf companions to brighter stars or planets orbiting their parent suns. The mathematics is well established. The instruments, at least in rudimentary form, already exist. In the deep future, when red dwarfs are some of the last visibly glowing stars in the cosmos, a black dwarf companion to a red dwarf would be a relatively easy detection. The red dwarf's slow wobble would mark the rhythm of the orbital dance. The mass of the invisible companion would emerge from the detailed shape of the wobble. The black dwarf would never be seen directly, but its presence would be unmistakable from the motion it imposed on its visible partner. The faint thermal emission method depends on the fact that the cosmic microwave background continues to cool. As the universe expands, the background cools steadily. In the very deep future, the background temperature will be far below a Kelvin. At that point, any object slightly warmer than the background, including a black dwarf with even a small residual internal heat source, will stand out against the cold sky as a faint thermal source. The contrast will not be dramatic, but it will be measurable, in principle, by sufficiently sensitive instruments. The black dwarf, by virtue of its long, slow leak of remaining warmth, would be slightly warmer than the cold cosmos around it, and it would, in that very specific sense, glow gently in the long wavelength infrared and microwave bands. This is one of the small ironies of the deep future. The universe gets colder and colder. The cosmic microwave background fades. The galaxies disperse. And against that ever colder backdrop, the cooled stellar remnants, the black dwarfs, the neutron stars, the stellar mass black holes, become, in a sense, the warmest things in the universe. Their warmth is feeble by any present-day standard. But against the unimaginably cold sky of the deep future, even a few degrees above absolute zero is a kind of glow. The black dwarf, in that distant epoch, becomes one of the most reliable sources of faint thermal radiation in an otherwise empty sky. Let your shoulders soften with that thought. The objects we have been describing are quiet, but they are not silent. They radiate gently. They affect light by their gravity. They reveal themselves in small, patient ways. The astronomy of a black dwarf cosmos would be, by necessity, an astronomy of patience, of long surveys, of careful measurements, of small, gentle signals carefully recorded. It would be, in many ways, the most peaceful kind of astronomy imaginable. There are a few quiet questions in the physics of black dwarfs that no one has yet been able to answer. They are not crises. They are not problems. They are the soft, unfinished places where the universe has left its long future story open. It is worth walking through them gently, because they are part of what makes the black dwarf so interesting as a subject. Not the certainty about it, but the small, patient uncertainties. The first is the question of proton decay. Protons are the small, positively charged particles at the center of every atom. Together with neutrons, they make up the nuclei of every element. Carbon, oxygen, iron, gold, all of these are made of protons and neutrons in different numbers. The fundamental question is whether protons are perfectly stable. If they are, then the matter inside a black dwarf is permanent on any imaginable timescale. The carbon and oxygen will remain carbon and oxygen forever. If protons are not perfectly stable, if they very slowly decay into lighter particles over enormous stretches of time, then the matter inside a black dwarf is, on long enough timescales, slowly evaporating. The black dwarf would, over an unimaginable span of years, gently dissolve from the inside. No one has ever observed a proton decay. Experiments designed to detect such an event watch enormous tanks of water, thousands of tons at a time, deep underground, and look for the faint flash of light that would accompany a single proton turning into a smaller particle. These experiments have run for decades. They have seen nothing. From the absence of detections, scientists can place a lower limit on how long a proton must, on average, live before decaying. The current limit is something like 10 to the 34th years. That is an enormous number, far, far longer than the age of the universe. Protons live, in this sense, almost forever, even if they do eventually decay. If protons do decay on roughly that kind of timescale, then black dwarfs have a slow internal evolution. Each proton inside a black dwarf has a vanishingly small chance, in any given year, of dissolving. Over a quadrillion years, the chance is small, but not zero. Over a quadrillion times a quadrillion years, the chance becomes appreciable. Over even longer stretches, the chance approaches certainty. On timescales of around 10 to the 37th years, the matter of a black dwarf would slowly sublimate into a faint mist of lighter particles and radiation, leaving behind essentially nothing. The black dwarf, in this picture, has a kind of half-life of its own, not a sharp explosion, just a gentle, gradual fading. There is a small, paradoxical detail to this picture that is worth noticing. If protons decay, then a black dwarf is, very slightly, warmed by its own decay. Each proton that decays releases a small amount of energy. Spread across the enormous body of a black dwarf, that energy keeps the surface very faintly above the cosmic background, perhaps by a few Kelvin, perhaps by even less. So a decaying black dwarf is, paradoxically, slightly warm. The fading itself is the source of its remaining heat. The same process that is slowly dissolving the object is also the only thing keeping it from being perfectly cold. If protons do not decay, if the lower limit measured by experiments is in fact a true infinity rather than a slow timescale, then black dwarfs are essentially permanent. Their matter would still slowly shift through extremely rare processes, piconuclear reactions in their interiors, slow tunneling of nuclei into one another at the quantum level, gradual rearrangements that on cosmic timescales would still happen, but only very, very rarely. The black dwarf would persist as a recognizable object for spans of time so long that the word long stops meaning anything useful. This is the first door left slightly ajar. Whether the matter of the black dwarf is, on the longest timescales, perfectly conserved or very slowly fading. Both possibilities are consistent with everything we currently know. Both are physical. Both are real candidates for what the universe is doing. The second door is the question of the black dwarf supernova. This is a quieter, more speculative idea, and it is recent in the physics literature. The reasoning runs like this. Inside the cold interior of a black dwarf, the carbon and oxygen ions are pressed against one another at extraordinarily high densities. Even at very low temperatures, the laws of quantum mechanics allow some small probability that two nuclei will tunnel through the electrical barrier that normally keeps them apart and fuse. This is called piconuclear fusion. It happens not because the nuclei have enough energy to overcome the barrier classically, but because quantum mechanics allows them, very rarely, to simply pass through it. Piconuclear fusion in a black dwarf is so slow that it is, for all practical purposes, undetectable on any human timescale. But over long enough cosmic times, even very rare events accumulate. Over inconceivable stretches something on the order of 10 to the 1500th years, the carbon and oxygen interior of a sufficiently massive black dwarf could slowly be processed into iron and nickel. These are the heaviest elements that can be produced by ordinary nuclear fusion. Beyond iron, fusion costs energy rather than releasing it. So an interior gradually working its way up toward iron is, in a sense, gradually emptying its remaining reservoir of fusion energy. Here is the interesting part. Iron is the most strongly bound nucleus. An iron interior cannot release any further energy through fusion or fission. And in a sufficiently massive black dwarf, one whose mass is near the limit that electron degeneracy pressure can support, the gradual buildup of iron may eventually destabilize the object. The electron degeneracy pressure that has been holding it up may, very slowly, fail. The interior may collapse, briefly and dramatically, in a way that releases an enormous amount of energy in a short time. The result, in this speculative scenario, is sometimes called a black dwarf supernova. If the universe ever produces such events, and the timescales involved are so long that "if" is the only honest word, they would be among the very last bright events in cosmic history. The black hole era would be drawing to a close. The dark era would be approaching. And then, very rarely, a small bright flash would appear somewhere in the otherwise empty cosmos, the slow accumulation of piconuclear fusion having finally tipped one black dwarf past its stability threshold. The events would be separated by vast stretches of nothing, like the last embers in a fire that has otherwise gone out. The black dwarf supernova is, today, a theoretical idea. It depends on a number of assumptions about how stable matter behaves in conditions no one can recreate. It may turn out to be wrong. The actual physics may forbid it. The timescales are so far beyond any verifiable scope that the entire scenario is, properly, a soft perhaps. But it is a beautiful idea that the universe might, in its very late old age, still produce a few quiet flickers of light, the last bright events of a cosmos that had otherwise gone dark. It is the universe taking one last gentle breath before the long stillness sets in. The third door is smaller, and it has to do with what we even mean by the end of a black dwarf. The cooling road we have walked is well understood. The arrival at black dwarf state is clear. But what happens after that? If protons decay, the matter sublimates over some enormous timescale. If protons do not decay, the matter persists indefinitely, modified only by extremely rare quantum processes. If the black dwarf supernova scenario is real, some black dwarfs end their lives in a brief flicker. If it is not, then they simply persist. There is, in a sense, no fixed answer to what the eventual fate of a typical black dwarf is. It depends on physics we have not yet confirmed. This is the soft uncertainty of the deep future. The shape of cosmic time on the longest scales depends on a handful of unanswered questions. None of those questions threaten the basic picture. The stelliferous era will end. The degenerate era will begin. The first black dwarves will appear. The cosmos will fill with cold remnants. All of that is on firm ground. What happens after, on truly unimaginable timescales, depends on protons and on quantum tunneling and on the speculative late physics of matter at extreme densities. Different choices give different futures. The universe has not yet finished telling us which choices it has made. There is a soft motif worth naming here. An unsolved mystery is not a problem to be feared. It is a place where the universe has left a door slightly open. Each open door is a small space for wonder. The black dwarf, as a subject, has at least 3 of these doors: proton decay, the black dwarf supernova, and the long-term fate of cooled matter, and each one is the kind of door that invites quiet attention rather than worry. In any other framing, these uncertainties might feel like incomplete physics. In this framing, they feel like the universe choosing not to over-specify its very long future. The cosmos is not in a hurry to commit. It has, very gently, left some of the late chapters of its own story unwritten, or at least unread, by us. That is, in a real sense, very restful. The universe is not insisting on a single ending. It is offering several possibilities, none of them violent, all of them slow. The future is not foreclosed. It is held loosely. The black dwarf, in whichever of these scenarios the universe turns out to inhabit, is the patient object at the quiet center of all of them. It cools. It settles. It exists. And whether it slowly fades or persists almost forever, it does so without urgency. So we can leave these 3 doors slightly ajar and let the future hold what the future will hold. There is no need to know tonight. There is no need to know in this century. There is no need to know in any reasonable span of time. The universe has many trillions of years to clarify its long-term behavior, and we are, again, very early. Let your eyes settle and your breathing slow with that thought. The patient endings are real. The shapes they will take are partly known and partly open. Both the knowing and the openness are part of the gentleness of the subject. There is room for the cosmos to surprise us. There is also room for it not to. Either way, the white dwarves of the universe are cooling tonight, and they will continue to cool for as long as is needed. It can help to sit with the speculative possibility of the black dwarf supernova a little longer, because it is one of the universe's loveliest, perhaps, thoughts. The idea is, by any reasonable measure, beyond direct verification. The timescale involved is so enormous, perhaps 10 to the 1500th years, that no plausible observation will ever confirm or refute it. The number itself is so large that ordinary scientific notation breaks down as a way of communicating it. To say it out loud, you would write the number 10 and then write 1500 zeros after it. The age of the universe today is, by comparison, 10 to the 10th year's just 10 zeros. The ratio between the two is unspeakable. So the black dwarf supernova is, in every practical sense, a theoretical idea about what very late physics processes might do in the absence of any other influences. It depends on assumptions about the stability of degenerate matter on timescales no laboratory experiment can probe. It depends on assumptions about quantum tunneling rates in conditions no one has ever recreated. It depends on assumptions about what happens when piconuclear fusion slowly converts the carbon and oxygen interior of a black dwarf into iron, on whether electron degeneracy pressure ultimately holds against that conversion or fails in the right circumstances, on a great many subtle physical questions that have not yet been settled. Each assumption is reasonable. Together, they produce the picture of occasional bright flickers in the very deep universe, the last fading sparks of a cosmos that has otherwise gone quiet. If the picture is correct, the events would be separated by enormous stretches of nothing. Most black dwarfs in the cosmos would never undergo such an event. Only the most massive, those just below the limit that electron degeneracy pressure can support, would be candidates. The lighter black dwarfs would simply persist quietly forever, or slowly dissolve via proton decay if protons decay at all. The events that did occur would be extraordinarily rare, separated by inconceivable spans of time, scattered across an inconceivably large volume of empty space. Any given observer, no matter how patient, would likely never see one. And yet, the cumulative picture is interesting. Over the very long span of time during which black dwarfs exist, the cosmos would, in this picture, produce a small but non-zero number of bright events. Each one would be one of the last bright events in cosmic history. Each would be a brief, intense flash in an otherwise unlit universe. The flashes would be separated by gulfs of time that dwarf anything we have so far considered. They would be, in this picture, the cosmos's last small celebrations of the kind of physics that once filled the night sky. Whether the picture is accurate or not, the idea is beautiful. It frames the deep universe as something that is not finished, even when it has, by every other measure, gone quiet. It suggests that the cosmos retains, even in its very late old age, a small capacity for surprise. It is not entirely without light, even when it should be. Even after the stars have all gone, even after the galaxies have dispersed, even after the black holes have begun their long evaporations, there might still be occasionally, rarely, gently, a flash. The universe holds on to its capacity for light, in this picture, until the very last possible moment. It is also worth noting that the calculation of these events depends on details that may be revised significantly as physics advances. The piconuclear fusion rates depend on quantum tunneling probabilities that are sensitive to the precise structure of the carbon-oxygen lattice, to the influence of trace heavier elements, to subtle corrections from quantum chromodynamics that are difficult to compute. The stability of iron-rich black dwarfs against gravitational collapse depends on the equation of state of dense matter at conditions we cannot reproduce. Different choices for these inputs give different estimates of the typical timescale and the typical event rate. Some calculations suggest the events happen more often than the figure we quoted. Others suggest they happen far more rarely, or not at all. The picture is real but unsettled. This is, in its own way, one of the gentle features of the subject. The deep future is not yet pinned down. The physics that governs the very longest timescales is still being worked out. There is room for the universe to surprise us. there is room for the calculations to shift. The black dwarf as an object is well understood. The very late physics of its existence is still being negotiated. Let your breathing slow with that thought. The cosmos does not require us to have all the answers about its very long future. The basic shape is clear. The patient endings are real. The stelliferous era will end. The degenerate era will begin. The first black dwarves will appear. The cosmos will fill with cooled remnants. Everything that follows, that the slow dissolution or the slow persistence, the rare bright flickers or the unbroken quiet, is still being worked out. The future is held loosely. The universe is allowed to surprise us. And the present moment, with all its warmth and brightness, sits comfortably outside any of the questions that matter for the very long term. It is possible, gently, to imagine standing somewhere very far in the future and looking back at our own era. From a vantage place deep in the degenerate era, the present universe would appear as a kind of cosmic morning bright, busy, freshly populated, full of glowing stars and turning galaxies and warm planets. The cosmic microwave background would be a comparatively warm 3 Kelvin, still detectable by the simplest instruments. The galaxies would still be holding their shapes. The Milky Way would still be turning. The sun would still be ordinary. From the far future, looking back, our present moment would appear unmistakably young. This is, in a real sense, the gentlest reframing of the entire subject. Black dwarfs do not loom over our present. They are not an approaching event. They are not a threat to anything we know. They are, more accurately, the natural late life form of the same kind of objects that already populate the night sky. The sun-like stars you can see tonight are not endangered by the black dwarf. They are simply on a very long path that eventually leads there. The path is unhurried. The destination is far. The present is, for all practical purposes, the very beginning of the journey. To an observer in the degenerate era, looking back at us, the black dwarf would not be exotic. It would be the most numerous large object in their universe. There would be billions of them in every former galaxy. They would be the cosmic equivalent of grains of sand on a beach, small, dim, cold, mostly indistinguishable from one another, scattered through enormous volumes of nearly empty space. The galaxies of that era would themselves be dispersing, slowly, over hundreds of trillions of years, as stellar encounters scatter their members into intergalactic space. A black dwarf, in that era, would most often drift alone, unbound to any larger structure, with the nearest neighbor at a distance much larger than any contemporary interstellar gap. The sky over a black dwarf in that era would be, by our standards, almost perfectly empty. The visible stars would be gone. The galaxies would either have dispersed or merged into dim ellipticals that themselves would slowly evaporate. The cosmic microwave background would be far below a Kelvin. The dominant sources of any signal in the sky would be the other black dwarfs, the neutron stars in their own slow cooling, the remaining stellar mass black holes, and the supermassive black holes that once anchored the centers of galaxies. The sky would not be black. Exactly, there would always be a small population of dimly warm bodies, but it would be quiet in a way that the present sky is not. In that deep future sky, the black dwarf would be ordinary. The exotic object, by contrast, would be the bright, young star, the kind of star our sun is now. From the perspective of a degenerate era observer, our present moment would be the cosmic anomaly, a vanishingly brief window of warm light in a long, cold history. They might find it remarkable that the universe was ever so full of glowing things. They might find the very idea of a sky lit by stars almost difficult to picture. The cosmic morning, viewed from the cosmic afternoon, would seem brief and luminous and easy to miss. There is something quietly grounding about that reframing. We are not late. We are not running out. We are, by every measure that matters for this subject, at the bright, early start of cosmic time. The patient endings are far ahead. Their absence is the natural state of where we are. The white dwarves cooling tonight will not become black dwarves for an enormous stretch of future. Everything we know about stars, about galaxies, about night skies, about the warmth of suns, all of it is the freshest version of itself. There is no decline. It is also worth saying that this very long view, while almost unimaginably large, does not collapse the present. It does not make the present meaningless. The cosmic morning is real. The sun-like stars are real. The galaxies are real. The light of every present star is, in a real sense, a kind of one-time event in the history of the universe, a glow that will not return once it is gone. Looking up at the night sky tonight is, in this very long view, looking at something the cosmos will never quite recreate. The same atoms will exist. The same matter will persist. But the present arrangement of warm, bright things will eventually be replaced by the patient arrangement of cool, dim things. That replacement is the substance of the long road we have been describing. There is one more soft motif worth holding here. The universe is not declining. It is finishing. There is a small but important difference. A declining cosmos would imply that something is being lost, or worsened, or broken. The actual long-term future is none of those things. It is, instead, a careful working out of the same physical laws that produced our present. The same gravity that holds stars together also slowly cools their remnants. The same nuclear processes that lit the early stars also produce the carbon and oxygen that fill black dwarfs. The same thermodynamics that allows stars to shine also requires them, eventually, to stop. The cosmos is not failing. It is, quietly, completing the very long thought that began with the Big Bang. That completion is what the black dwarf is. It is the patient end of the sun-like star idea. It is the universe finishing the thought of every ordinary star. It is the calm, expected, structurally permanent outcome of the same physics that lights every sun tonight. And so we come back, gently, to where we started. The black dwarf is the cooled-down body of a sun-like star. None exist yet because the universe is so young that even the oldest white dwarfs still glow. The first ones will appear in the degenerate era, when the cosmos itself has matured beyond the bright early phase we now inhabit, is less than #0. 5 # is greater than the sun is on this road. So is every other ordinary star. The path is long and quiet. The destination is real and far. The present is the cosmic morning. The black dwarf is the patient evening. You might, listening to this, feel a small softening in the way you hold the night sky. The cosmos is not in trouble. The cosmos is not running out. The cosmos is, in fact, only just beginning. Every star you can see is in its earliest hour. Every white dwarf hidden behind interstellar dust is in the first 100,000th of its cooling road. The patient endings are real, and they are inevitable, and they are also so far ahead of us that nothing about them touches the present. This is, in a real sense, what the black dwarf is for, as a subject. It is the universe's longest exhale. It is the most patient, single thing the cosmos knows how to do. It does not insist. It does not hurry. It does not ask the present to be anything other than what it is. It simply waits, very quietly, very far away in time, for the slow cooling of the white dwarves to bring it about. And in the meantime, the universe goes on glowing. Let your shoulders soften. Let your eyes settle. Let your breathing slow. The white dwarves of the cosmos are cooling tonight. The sun is shining outside, somewhere on the other side of the earth from wherever you are listening. The galaxies are turning. The patient endings are in their place, very far ahead, waiting calmly for the cosmos to walk toward them on its own slow schedule. There is nothing you need to do. There is nothing the universe needs to hurry. The black dwarves will come, in their time, in the deep quiet of the degenerate era, when the cosmos has finally aged enough to make them. Until then, the morning continues. The light continues. The slow road continues. And every white dwarf in every galaxy in the observable universe is, in this exact moment, taking one more very small step on the long, gentle journey toward that patient ending. And so we leave the black dwarves, where the universe is still slowly making them, not in the night sky above you, but in a long, quiet future that no eye will ever quite reach. Every white dwarf cooling tonight is taking its first soft step on that long road. The road is unhurried. There is no need to follow it. Let your breathing slow. Let your shoulders soften. Let the night settle around you like the deep, patient dark of a much older universe. Sleep well, and good night. Before we let the night settle fully, it can help to gather, gently, the threads of this long walk. We began with the basic fact that black dwarves do not yet exist, and we have walked, slowly, through why. We have looked at what the body of a black dwarf is made of, the carbon and oxygen interior, the crystalline lattice, the electron degeneracy pressure that holds it up, the Earth-sized sphere holding a star's worth of mass. We have walked the long, cooling road from the hot, white dwarf, through every color of starlight, into the infrared, into the far infrared, into the very long thermal tail that finally arrives at thermal equilibrium with the cold sky around it. We have set that cooling against the deep future eras of the universe, the primordial, the stelliferous, the degenerate, the black hole, the dark, and we have placed the first arrivals of black dwarves in the degenerate era, after our own present moment, by a stretch of time so vast that the word vast itself becomes inadequate. We have followed the sun through its own version of the road. We have watched the present main sequence sun age swell into a red giant, engulf Mercury and Venus, possibly engulf Earth, exhale a planetary nebula, and leave behind a small white dwarf core that will cool through every color and every phase until it finally, after a quadrillion years of patient descent, becomes a black dwarf. We have noticed that the outer planets may survive, that one or two might even remain bound to the cooling sun, and that the black dwarf sun of the very deep future may still have quiet companions in slow, distant orbits. We have looked at how a black dwarf might be observed, even though none exist. We have seen that gravity remains the universal signal, even for cold and silent objects, and we have walked through the methods microlensing, binary companions, faint thermal emission, crystal structure signatures in the cooling curves of present white dwarves that would form the astronomy of a black dwarf cosmos. We have noticed that the non-detection of black dwarves today is itself a finding. The universe is precisely on schedule. The arrivals are real and on their way. They are simply not here yet. We have set down 3 soft doors left slightly ajar proton decay the speculative black dwarf supernova, and the long-term fate of cooled matter. And we have noticed that none of them threatens the basic picture. The cosmos is allowed to surprise us in the very long term, but the patient endings are themselves secure. The future is held loosely. The mysteries are gentle ones. And we have, finally, taken the view from very far ahead. We have imagined an observer in the degenerate era, looking back at our own moment as a cosmic morning bright, brief, full of warm, glowing things, a small early chapter in an enormous and quiet story. We have placed ourselves carefully in that picture. We are at the beginning. We are not late. We are not running out. We are in the very first early hours of cosmic time, and everything we know about night skies and warm stars is the freshest version of itself. You might let yourself sit with the soft truth of that for a moment. The cosmos is unfinished in the gentlest possible way. The patient endings are real and inevitable and far away. The first black dwarf will arrive when the universe has aged into a form we would not recognize. Until then, the sun rises and sets. The stars glow. The galaxies turn. The cosmic microwave background still carries its faint warmth from the very early universe. The white dwarves of every galaxy continue their slow, patient cooling, one tiny, imperceptible step at a time, on a road that takes 100,000 times the current age of the universe to walk. There is nothing about any of this that asks anything of you. There is nothing about it that needs to happen tonight, or this year, or in this lifetime, or in this geological age, or in this cosmic era. The cosmos is, in its enormous patience, walking the road for itself. The black dwarves will come in their time. The morning continues. The light continues. The slow road continues. And every white dwarf in every galaxy in the observable universe is, in this exact moment, taking one more very small step on the long, gentle journey toward the patient ending. So let your shoulders soften. Let your eyes settle. Let your breathing slow. The cosmos is in no hurry, and there is nothing about the night that asks you to be in one either. The patient ending is real, and real far. The cosmic morning is here, around you, doing what it has always done. The stars are out, somewhere. The galaxies are turning, somewhere. And the universe is, very gently, taking its time.